Here's a related rates problem for you to try yourself. Let's take a look. Allison and John leave Danny's house at 2 p.m. Allison is driving north at 25 miles per hour, and John is driving east at 30 miles per hour. How fast is the distance between them increasing at 2:30 p.m.? So here's a little picture of what's happening. Here's Danny's house, and at 2 p.m. John travels this way at 30 miles per hour. Allison travels north at 25 miles per hour. So clearly the distance between them is increasing as time passes. So let's pause the video and you can try and do this problem on your own. Let's see what happens a little later, just a little bit after 2 p.m. Well, we see that John has traveled some distance, Allison has traveled some distance, and so let's label those. Let X be the distance that John has traveled, Y be the distance that Allison has traveled, and let's let S be the distance between John and Allison at some later time t. Well, we need, remember, for a related rates problem, some kind of relationship between the variables and their rates of change so that we can determine what we want to know. Okay, so what is that relationship? Well, it's the Pythagorean theorem. So we have x squared plus y squared is equal to s squared, and now we'll pause the video again so that you can see if you can determine a related rates equation so that you can find how fast the distance between them is increasing. What would that be? That would be ds dt. Well, let's go ahead and do the derivative of both sides of the equation with respect to t using the chain rule. So here we get 2x, but because x depends on t, it changes as time changes. We have to multiply by the derivative dx dt, similarly plus 2y dy dt is equal to 2s ds dt. So now we have an equation that involves ds dt, but we have to know what all these other values are. Well, we can cancel the 2's, that's easy, but let's see what's happening at 2 p.m. At 2:30 p.m., that's 1/2 hour later, so time is 1/2, so the distance, x, is the rate, which is 30 miles per hour, times the time, which is 1/2 hour, so x will be 15 miles at 1/2 hour. Y will be 25, the rate, times 1/2 hour, which will be 12.5 miles. So we can fill those in and try to solve once again for ds dt. Let's look at the triangle. At 2:30, we have 12.5 and 15, as we determined before, and here's s. How do we find s? Well, again, we use the Pythagorean theorem. 12.5 squared plus 15 squared equals s squared, and if we do the calculation here, we see that 381.25 is s squared, so s is equal to the square root, of course the positive square root, because this is a distance, of 381.25. And now we can go back to our equation, plug in the things that we know, and finally solve for ds dt. So let's pause one more time. Now let's finish up, remembering that we were able to cancel those 2's, and let's substitute all of the values that we had for 2:30 p.m. So remember, x was 15 and dx dt was 30 miles per hour, plus y, that was 12.5 times dy dt, which is 25, is equal to s, which was the square root of 381.25 ds dt, and it is ds dt that we want to solve for. So now we can go ahead and do that. We have ds dt is equal to 450 plus 312 doing the multiplication, 0.5 over the square root of 381.25, and that is approximately 39.05 miles per hour. And that is the rate at which the distance between Allison and John is increasing at 2:30 p.m.